Hello everyone, today we have some improper integrals and we are interested in the limit case. So this fraction is integrated 0 to infinity and then it depends on n and we want to take limit as n goes to infinity. So I begin the solution by making some observations about the nature of this fraction. So number one, it is the fact that it has no singularities. So the singularity is actually in the bounds of the integral, which is from 0 to infinity. Indeed, for every x, for every n, and by that I mean x in the range of interest here, we have that the fraction cosine xn 1 plus x to the power n in absolute value is bounded by, so I put the largest numerator, which can be 1 because it's a cosine, and the smallest denominator will be when I have 0. So that makes it a 1. So this is a continuous function bounded above by 1 in absolute value. So we will come back to this fact soon. The other observation is that xn's converge uniformly to 0 on intervals from 0 to some 1 minus delta for any delta positive. And that will be a key part of computation. So fix delta positive. And usually we want to think of it as pretty small, so much less than 1. Then xn converges uniformly, so I use these double arrows as emphasizing that it's a uniform convergence on 0 to 1 minus delta. Which is quite famous. Well, the biggest will be 1 minus delta to the power n, and that goes to 0 if n goes to infinity. So as n goes to infinity, these xn's uniformly converge to 0. So cosine of xn divided by 1 plus xn, notice that xn's are away from -1, absolutely having nothing to do with that, with the 0 of the denominator here. So it follows that this converges uniformly to just plug in 0 here. So you can prove that if you compose a function with a sequence of functions that uniformly converge, the result will also converge uniformly. So this will be 1. So on the interval from 0 to 1 minus delta, this fraction uniformly converges to 1. And as a result, because we can pass inside the integral sign, so integral from 0 to 1 minus delta of cosine xn divided by 1 plus xn dx as limit n goes to infinity will be, so this has nothing to do with an improper integral or anything. These are bounded compact intervals, everything is nice, you have continuous functions in the interior, and because they uniformly converge, you can pass the limit to the inside of the integral sign, but that inside converged to 1 as we just saw above, so this will be 1 minus delta. So that's one thing we want to keep in mind for later, that we computed the limit from 0 to 1 minus delta. Okay, the second observation is that if x is bigger than 1, then x to the power n in the denominator converges to infinity. And the numerator, of course, cannot beat that because it's bounded by 1, so everything converges to 0. And we expect to have a 0 integral for that part. But it's a little bit trickier because even if you have uniform convergence to 0 after 1, you cannot simply pass to the limit in the inside because you're dealing with an improper integral. So to alleviate this problem, we do the following. So I want to look at integral from 1 plus delta. So I want to avoid 1 because near 1, xn does not converge uniformly. To some L, okay, so for every L bigger than 1, say, 1 plus delta to L cosine xn 1 plus xn dx, the absolute value of this will be less than from 1 plus delta to L. I want to be generous and give the numerator a 1. In the denominator, I get rid of 1. So that also becomes quite large. So everything is helping my fraction. Every change that I made here is helping my fraction. So I put an upper bound here. And this, it has an easy antiderivative. So I will get 1, negative 1 over n minus 1. 1 over x to n minus 1. And then I plug in 1 plus delta, I plug in L. And actually, if I put L infinity, I get a larger value. So for an inequality, I will get 1 over n minus 1, 1 over 1 plus delta to power n minus 1. So here I'm also assuming that n is not actually equal to 1, which is okay because I'm interested in the limit case anyway. So we have this inequality, and this is for every L. So since L was arbitrary, integral from 0 to infinity, not 0, so from 1 plus delta to infinity of cosine xn divided by 1 plus xn dx, which by its very definition is limit L goes to infinity of 1 plus delta cosine xn divided by 1 plus xn dx. Now if I put absolute value here, then this is absolute value here, and we saw above that no matter what L is, these integrals are bounded by 1 over n minus 1, 1 plus delta to n minus 1. Okay, and this will show, so limit as n goes to infinity of the integral 1 plus delta to infinity cosine xn 1 plus xn dx is 0. So as we wanted. So the two computations that I did, first on the interval 0 to 1 minus delta, and this one that you see right now, are sufficient, in fact, to give us the final answer. So what happens is, again, for every delta positive, integral from 0 to infinity cosine xn 1 plus xn dx will equal from integral 0 to infinity 0 to 1 minus delta of cosine xn 1 plus xn dx plus integral 1 minus delta to 1 plus delta of cosine xn 1 plus xn dx plus integral from 1 plus delta to infinity of the same fraction. So this is an obvious equality. For every n, this is true, and for every delta. I simply broke up the interval. And notice that except for the last integral, everything is just some bounded compact domain. So this is all okay and justified. So what happens then is that if I call this quantity, this integral here, I, if I call this integral 1, 2, and then there is the third integral here. So I have shown several things. So if limit n goes to infinity of I, we showed equals 1 minus delta. We showed that limit n goes to infinity of the third quantity is 0. On the other hand, we see that the second one is bounded by length of the interval on which we integrate, which is 2 delta. Remember that this integrand is bounded by 1, so the integral will be bounded by 1 times the length of the interval, which is 2 delta. So the quantity in 2 is always bounded by 2 delta. So when we put these together, it shows that if we let delta now go to 0, then we are done. So because we have 1 minus delta 0 and an error term bounded by 2 delta, and delta is arbitrary, so we are left with just 1, and that's what we wanted to show. So if you have any questions about any part of this solution, please write in the comments. Don't forget to subscribe, and thanks.